tables that were missing, so you can at least do part 2. I know some of you are having difficulty with the CACT part. I have office hours tomorrow at 11 a.m. I know that I said I would update the other times, and I haven't yet done that, so I apologize, but I will have some other times as well. That I will get the syllabus corrected and updated so that you can reach me if that time doesn't work for you. I think, how many of you have gotten it to compile? Let's see, I've gotten a few messages. I think I owe several of you replies, and I'm working on working my way through all those to try to help through email if I can, but it may be easier if we do it through Zoom or something. We can try to work through whatever's going on. And I assume you all saw campus is virtual tomorrow, and I don't know what that means for, they don't consult me on these decisions. It seems kind of weird that tomorrow is closed since it's going to be warmer than it was today.
Are you sure? Because I saw the temperatures in the next few days are gonna go a little bit of freezing. I don't know. Because
yeah,
because the polar winds.
If they're not going to have school tomorrow,
Not only online, but
on virtual school, I mean, not going to have campus open. Tomorrow it's like between 20 and 29, but then that's the warmest it's going to be like for a week. Next Monday it's predicted to be -2, and next Tuesday it's predicted to be -5.
I think it's based on precipitation, not just how cold it is. We've gone to class when it's that cold. So I'm guessing they're expecting more ice build-up to be on the roads or something like that.
Yeah,
Which I haven't seen because it's not raining outside.
right. It's not supposed to rain, but certainly -5. I can understand.
I mean, at that point, that's
the
just,
wind chills are going to be real
Yeah.
low, and
I mean, the wind chill I think was at like -20 or -30, something like that.
so who knows? When we'll be back on campus, if we'll have class in person on Thursday. Obviously, if campus is open, then we'll have class in person, and if it's not, then we'll have class via Zoom. But we'll make it work either way. So just watch for that. But if they're canceling tomorrow, like it seems likely moving to virtual tomorrow, it seems likely that there'll be some other days that are moved to virtual as well. So we're going to pick up where we left off. Like I said, the homework's due Friday now. I will assign another homework on Thursday, so we'll get back on schedule, but for now, at least you have the rest of the week to work on either the CAPT part if you're having trouble with that, or the 2 parts that were just impossible to answer on the cash homework because you didn't have the tables to go with them. So we've discussed before, but when we look at our cash organizations, we're looking to capture 2 different types of locality, meaning 2 different types of patterns of access where we have reason to believe that either the same location is likely to be used again, soon, meaning, likely to be accessed again, in some short amount of time, relative to the likelihood that some memory location that I haven't yet accessed, or maybe I've accessed a long time ago, then I might believe those other locations would be not likely to be accessed. So maybe, as just one example, there could be lots of ways in which temporal locality is realized, but one way might be that we have some variable in our program that's read and written inside of the loop. And so maybe every loop iteration, we're using the value of that variable. Maybe we're updating it every time, and we're doing it over and over and over. And some variables, might be just completely held within registers within a loop, but we know that we only have a finite number of registers in whatever processor that we're talking about. And so the big picture of where data and instructions reside is that they reside in memory. And so we may optimize some kind of access where we would put the variable in a register, and then we wouldn't have to go to memory, we wouldn't have to look for those variables in the cache every loop iteration, but maybe we have 16 variables in our program, and we only have 12 registers that can be used to hold sort of general purpose values at any given time. Another example, instructions, we know that most of the executions of real programs reside within loops, otherwise programs wouldn't run very long. And so if we have a loop and it's going to execute 1,000 times, then we're going to fetch the same instructions over and over again from our instruction cache 1,000 times. So we know there's a high degree of temporal locality for those instructions. And we don't have to have a loop for temporal locality to exist. We might have some sequential computation where we reuse, or where we access either reading several times or reading and writing a particular variable. And so we're continuing to use that memory location multiple times. And then maybe we move to a new phase of the program and we don't read or write that particular variable for some longer amount of time. And so during the time when we're reading and writing it, we have a lot of temporal locality, and then eventually it becomes something that hasn't been used in a long time, and we'll want to replace that in the cache. And we left off talking about spatial locality, but and the idea is that if we access a particular memory location, then the adjacent memory locations meaning that that memory locations with addresses that are nearby that location that we accessed are likely to be accessed soon. So one example that would be a common expression of spatial locality would just be an array. We know if we access element 0 of an array, chances are we'll access soon element 1 and then element 2, etc. Similarly, in terms of data structures, if we have some type of object of some class that has several fields, if we access one of the fields, we'll probably access the other fields as well. And so hopefully I've convinced you that there are, patterns in typical programs where both temporal locality and spatial locality exist. And hopefully it's also kind of apparent that these just indicate that there's a likelihood that these memory locations might be important. They don't guarantee it. And different programs have different degrees of temporal locality and spatial locality. And so, a really numerical, computation intensive, linear algebra type of application may have a lot of spatial locality, where some irregular integer application with no arrays at all may have less spatial locality. They probably still have some. And we know that, in a typical implementation, elements of an array are going to be located in adjacent memory locations, and the fields of an object are going to be dynamically allocated such that they're going to be also in adjacent locations. All of the objects fields are all co-located together. So we know that we've kind of designed the way that our cache works by caching locations that we've used because we believe that we'll use it again in the future. We know that that's going to take advantage of temporal locality. Also, the replacement approach that we've been talking about, least recently used, is going to take advantage of temporal locality, meaning if we've used it recently, we think it's more likely to be important soon than something that we haven't used in a long time. So that gets us to how are we going to take advantage of Alt for trying to move it. How are we going to take advantage of spatial locality with the way that we organize our cache? And what did we say? What was the idea when we left off?
Add multiple blocks to each way.
Uh,
Add multiple words to each block.
Yeah, so we're gonna make our blocks larger. Where initially our examples have all assumed 32-bit blocks, assuming a 32-bit word, where each block was just a single word. So every time we loaded value, that entire value would be placed into the cache. Because of spatial locality, there's, and, well, we can talk about other reasons too, but, spatial locality alone would tell us that there might be benefit to, instead of just grabbing a single word in memory, to grabbing some adjacent words as well, and to read more data from the memory than just one word. So I'm hunting for the on switch, there we go.
The projectors are still on.
Yeah, I made the mistake of turning that off, which I shouldn't have. But now I think it's all warmed up, and we're back in business. And so that's what happens when you unplug it. So we can stay with the same size cache, but now think about, instead of having 4-byte blocks, we have 8-byte blocks. Something like this, where I've drawn just this dashed line to indicate the division between two 4-byte words. So each block consists of a total of 8 bytes. And so we have 4 bytes and 4 bytes. They make up the same block in index, with index 0, in either way 0 or way 1, because we said it was two-way associated. Since our blocks are now 8 bytes, how many bits of index do we need to refer to the individual bytes within our block? 3. So we had 2-bit indices when we only had 4-byte blocks.
Are you referring to offset?
Yes.
Alright. You said index.
My apologies.
Alright.
The offset of the individual byte within the block. And we know that we need 3 bits because our block size is 8, and log base 2 of 8 is 3. And if we wanted to divide up the offset, you know, initially the last 2 bits told us the byte within the word. The additional bits of the offset are going to tell us which of the words that we're interested in. So you could call it a word offset and a byte offset, but we'll just call the whole thing the offset. For the cache as drawn, how many bits will we need for the index? We only need 1 bit for the index because we only have 2 sets. Remember when we had the same 32-byte cache, 2-way associative, but when we had 4-byte blocks, we actually had 4 sets because each set contained only a total of 8 bytes. Now each set contains a total of 16 bytes because we've got 1, 2, 3, 4 4-byte words. And then we know the rest is all going to be the tag. And again, since we have 6 bits of tag, we know that there are 2 to the 6 or 64 different 8-byte blocks in main memory that have index 0 and 64 8-byte blocks that have index 4.
Are you still going to be scanning these and uploading them?
Yes, I apologize, I didn't have to yet, but I will. So if we loaded address 64, we're going to even if we only do a 4-byte load, we're going to load from memory 8 bytes. Or in other words, we're going to load both the words that start with 64 and the word that starts with 68. One of the reasons that we want blocks that are bigger than just a single word would be that if we're loading 64, we think that there's a likelihood that 68 will be used again in the future. But there's another reason that we get benefit from loading more than just a single word from main memory. Remember, what's the problem with main memory? What performance metric is poor about main memory?
Response latency.
Latency, right? Latency is long to go out to main memory. But even though the latency is long, if you look at the specs for, your expensive memory that, you buy for your gaming rig, it's DDR3, whatever it is, 4, what's the metric that it is high, that is better? If latency is poor, because it's sort of fundamentally difficult to build really dense memories that have really low latency. But we can make it have relatively good what?
Speed or bandwidth or something like that.
Yeah, bandwidth was what I was going for. And so the idea would be, it may take many nanoseconds to get this word, but to get this adjacent memory location, it's basically free to bring it from memory. And so we can bring, because our memory is designed with a relatively high bandwidth, we can bring big chunks of memory into the cache relatively quickly once we start to get the first byte returned from the access that we're going for. So we can take advantage of the high bandwidth to try to hide the future latency of accessing these adjacent locations. Sometimes students get fixated on the idea that we're always taking the next word, but that's definitely not the case. So if we load address 100, we're going to get all 8 bytes for all the 8 possible values for this offset. And so what's the lowest address byte that we're going to get if we load address 100?
96.
Yeah. So we're going to load bytes 96, 97, 98, 99, 100, 101, 102, 103. Even though we loaded 100, we're going to get this adjacent location that's on the lower side of the address space. And we know, spatial locality works in both directions. We might maybe tend to write programs where we go forwards through arrays, but you could just as easily go backwards. And if it's some other memory location, like a field in an object or a struct, earlier fields are probably just as likely to get access as later fields. probably don't sort your fields by the order in which you load them or something. So we're gonna get all 8 bytes, starting with the address that ends in 000 and all the way to the address that ends in 111. Questions about increasing block size? We'll go through to kind of make sure we can calculate which bits are used for what. For arbitrary sizes of caches and associativities of block size, etc.
In practice, what block sizes are normally used?
Usually it's in the range of 64 to 128 bytes, and usually the lower cache maybe like 64 and the L3 maybe 128. I mean, you could get bigger. What's the advantage of bigger blocks?
More forward looking, more backward looking. You get more information.
Yeah, so.
You get it for less cost because you can stream it straight from there.
Right, so in a typical level 1 cache, if it's 64 byte blocks, I'm only doing one load, but I'm gonna bring in 64 bytes at a time into my cache. And so that means if I do actually access all of those elements, say I'm going through the elements of an array, I'll miss the very first element, but then the next 15 elements, if they're all 4 bytes, are gonna be hits because I suffered the latency once, brought the whole 64 byte word into the cache, and then the rest ones will be hits. If I had made it 128, then I would have had 1 miss, and then the next 31 would be hits. What's the downside with bigger blocks?
Less random positions. They're more sporadic.
Right. So, this is a really simple cache, that doesn't have a practical use maybe, but we saw doubling the size of the blocks, now we have half as many blocks as we had before. And so you wouldn't want to make your blocks too big because then you don't have very many blocks. And so like you said, you wouldn't be able to cache as many different locations. And so there's definitely a trade-off in sizing. Since caches are now, reasonably big, you can have reasonably big blocks. You probably also expect that there is some diminishing returns in terms of in terms of spatial locality, that maybe something 1,023 bytes away may not be super highly likely to be necessarily accessed soon, compared to something that's 32 bytes away.
Diminishing returns, basically.
Yeah. And so, the optimal hit rate is going to be a function of your program, but also a function of the size of the cache. So the bigger the cache, you can afford bigger blocks. We will talk about, when we talk about multi-processor caches, we will talk about inclusion. And one of the nice qualities, but it doesn't come for free, of a memory hierarchy is to have what's called inclusive caches, where you guarantee that the bigger, farther away caches always contain everything that's in the smaller, closer caches. For caches to be inclusive, then the bigger caches have to have at least block sizes that are the same size or larger. And so usually they'll be, a multiple of the, if it's going to be bigger. And so that'd be one of the requirements to make it possible to be inclusive. But there are weird and sort of unfortunate costs to making it inclusive, but it is nice if everything that's in L2 is also in L3, and everything that's in L1 is also in L2 and L3. But it doesn't just always magically happen.
Have we covered yet when you write stuff out to memory from, like if we change up any cache?
Nope, but that's exactly what we're about to discuss. Before we do that, any questions about spatial locality? So before we talk about stores, just to make sure we're explicit about calculating number of bits offset. So with larger block sizes, we'll need larger offsets, and we said the offset is just log base 2, the block size. How many bits of index do we need? It's a function of what? Log base 2 of?
The number, not blocks, but rows, I don't know what you call them.
Right, and so we call those sets. So log base 2, the number of sets, gives us the bits of index. The tag is really everything else, but remember this is also so these should be the same. And here we say blocks in memory, but it's the number of blocks in our memory address space. So if we have 64-bit addresses, it may not all correspond to actual memory locations which we can store things, but that tag is going to represent how many different addresses in memory correspond to blocks that would have the same index. And it should be log base 2 of that, will give you how many bits of tag that you need. And again, it should just be the size of the address minus the bits that are used for the offset index. In the index, you need to know how many sets there are. Remember, the number of sets is just the total number of blocks in your memory divided by the associativity. Often when you get the parameters for a cache though, you're going to get the cache size, the block size, and the associativity. So how do you figure out how many blocks you have?
The cache size divided by the block size.
Exactly. And so this should work for any size of blocks or associativities, at least that are powers of 2 to use the log base 2. Any questions about this before we move on? Alright, so seeing none, let's start with So I've asked two questions here. The first is, should we treat store misses, I'm sorry. That was going too fast. And the question is, store misses, should we treat them the same as load misses? So we know if we load a value from memory, it's not in our cache, we're gonna put it in our cache, because we believe we're likely to load it again. Should we do the same for store misses? Remember, can we cache, say we have a 64-byte block, can we cache just an individual word, an individual 4 bytes? What's the granularity at which we cache things? It's the block size.
2 words.
So we have to cache the entire 64-byte block. We can't just cache 4 bytes by themselves. We'd have to get the whole block. And so if we're storing to 4 bytes, but our block size is 64 bytes, that new block represents 4 bytes that have changed and 60 bytes that are the same as what's in memory. So if we're going to cache that block, we're going to have to get the rest of the block, the other 60 bytes. What are we going to have to do? Where do those other 60 bytes reside?
In main memory.
In memory, right? And they're in the next level cache. So if we want to cache locations when we have a store that's in this, we're going to have to first load. I mean, the processor is going to actually have to load from the next level cache or from main memory the entire block so that it can cache that block, and then it will update the bytes that we're storing to. And so if we have 64-byte blocks, we're going to have to load 64 bytes from main memory, and then we'll store, maybe our store updates just a word of 4 bytes. We'll update the 4 bytes that have changed, and the rest will match what's in memory. So it's a little weird that to do a store, we have to first do a load, and then we can store. And so the question is then, should we do this? What's the alternative?
Just writing directly to main memory, like sending that command.
Right. Yeah. We could just say, it wasn't in the cache, we're just gonna go update main memory, the 4 bytes that we're changing, and then we can just, go on with our program. And so the two choices are, either write allocate or write no allocate or write non-allocate, where yes,
What's the difference between no allocate and non-allocate?
just another way to say it.
Ah, okay.
So
Yeah, yeah.
also known as write non-allocate.
Yeah.
I love these kind of questions. For let's see, for all programs in the world, is there one choice that would be the best?
Not for all, would it be a choice that would be good for some, but bad for others, and the other choice would be good for others.
Right. So I could write a program where I store to memory locations and then never turn around and load them. And so there'd be no benefit in caching when I store, because I'm always just gonna turn around and store something, load to other locations and never go back to the thing that I stored. Or I could have a pattern where I store something and then pretty soon load it back, or load back the adjacent locations. And so depending on those patterns, the latter pattern, right, allocate, would perform better. The earlier one, if I don't reuse the locations that I store to, there'd be a benefit to not allocate. Typical programs have a relatively high degree of temporal and spatial locality for stores, but it is somewhat less than that that exists for loads. And so this would be, one of the design choices that you have to make for your cache, and there isn't necessarily one that is better than others. This one is probably simpler in terms of complexity, because it doesn't require you to first load the block into the cache and then update it, versus this one that does require it. So you bring the whole block into the cache first. Questions about those choices and like under what conditions one would be better or not? The next part of the store discussion, there is a more clear-cut winner, but again, there's always a trade-off. So this has to do with misses. If we miss, we're either gonna bring the block from memory into the cache, and then the cache will get updated to make sure it reflects what we stored, or we won't, we'll just update memory. So, say we have a store hit. The location that we're writing is in the cache. We know if it's in the cache, we're gonna update what's in the cache. Do we also go ahead and update memory so that the cache and memory match?
Not necessarily. In fact, not super often.
So what's the benefit of waiting?
It's pretty common if you're iterating through a loop, to repeatedly update the same variable over and over, and there would be no need to write that back to memory every single time.
Right.
If you had an accumulator or something.
Similarly, we might store to the other bytes in the same block, and we might be able to get away with writing that whole block to memory once rather than 64
if you're writing
times.
an array and you're
Right,
writing
if you go
through
through the array, we could have one write of the whole block versus a bunch of writes, one after another to make it. So we have two choices. We can update memory immediately. That's probably the simplest thing to do. So we know that every time we have a store, the value in memory matches the value in our cache. And whenever we overwrite a block, or wherever we replace a block in our cache, we can always just throw away what's in the cache because we know it's an exact copy of what's in memory. But we've given some reasons why we think there may be benefit to waiting. We might be able to amortize the cost of storing to main memory by just doing it once for a whole bunch of stores. Versus here, every time we do a store, there's a write to memory. And so there's a good reason to believe that in general, this would perform better. Now, when we do this,
We won't need another flag for every block to say to write it back, right?
right, so. We don't want to write back every block to memory every time we replace a block. We only want to write back the blocks we only want to write back the blocks to which we've stored. And so like he said, we'll want a flag on each block. And typically it's called the dirty bit, and sometimes, I don't know, students find that amusing and giggle. The dirty bit is going to tell us if it's a 1 or if it's set, that this block is dirty, meaning that the contents of this block don't match what's in main memory. If it's just 1 bit, does it tell us which bytes are dirty and which ones are clean?
No, you have to write the whole block.
You gotta write the whole block because we don't know, it could be just 1 byte has been changed. We might have done a store byte and just changed 1 byte, or we might have written every word in that block and we might have written it 75 times. We don't know, we just know that there's at least been 1 write. And so whenever we have a store that is a hit, or in the same way, if we had a write allocate cache, we're storing and the block has been brought into the cache, we update what's in the cache. If we're gonna do write back, we're gonna mark that block as dirty, and we're gonna update the cache, but we're not gonna update memory right away. If we're a single processor, when we go to load those bytes, we'll load the cache first, we'll load from the cache first, and we'll get the most recent value for that memory location. Eventually, because the cache is smaller than main memory, eventually we're gonna have to replace that block and we'll write it out to memory at that time. But we won't have to write it out to memory until that occurs. And so if you think about now, for every block we have a valid bit, we have a dirty bit. If it is write back, if it's write through, we don't have a dirty bit. We have bits for replacement. So if it's LRU replacement, then we have log base 2 of the associativity bits for each block to keep track of where it is in the replacement order. We have the tag. And so we have all this sort of metadata about the block that's in the data array. Or you can think of it as bookkeeping. all this bookkeeping that we have to keep track of for the block that's in the array, in the data array. Thoughts about write back or write through?
I guess that's not the question when you start dealing with multiple cores or multiple programs. How do you deal with one program write to one bit that happens to be in the same cache block that another program wrote, and if they're in two separate caches, you get overlap issues.
Right. And we are going to pick up with that. We can kind of talk at a high level about that right now. But that would be one reason why we might have, for our level 1 cache, a write-through policy, because the stores aren't actually written all the way to memory. They're going to write to L2, where L2 and 3 might be right back. And the question then will be, which caches do we keep what we call coherent, meaning all the processors see the same value for a shared memory address. So in general, we would expect which of these to perform best, just in terms of, you know, the performance. If we had a single processor
Write back.
we'd assume write back would perform best. I mean, I could write a pathological case where write back does no better, and then I guess with the additional complexity and cost, write through would have been better. But a typical program, we're going to expect write back to do better. But we can see write through has less cost because we don't have the dirty bits. And we don't have to worry about we don't have to worry about writing blocks back to memory if they've been changed, regardless of whether they've been changed or not. Any other thoughts about this? And then we'll kind of leave with some discussion about multiprocessor. And we're going to discuss later more about how modern processors are interconnected. But let's start with just a very simple processor picture. Something like this, where we have some number of processors that are connected to memory via a shared bus. This is sometimes called a symmetric multiprocessor because if we're standing here and looking at memory, looking from memory, all the processors look the same. Basically, all of the processors are this would also be all the processors are the same distance from memory. It's a uniform memory.
Is this saying that the processors are all directly connected to memory, and there is a cache intermediate layer, or is the memory saying the cache and memory is right there?
So I haven't drawn the caches yet.
Oh, okay.
And so we'll add the caches in, and then we can discuss the implications. For now, if we didn't have caches, this would work. We can have shared memory programs. You know, how many of you have written multi-threaded programs? And in those, have you had shared memory locations that all the threads can see?
Yeah.
And then also maybe thread private locations that only one thread can write or read. So if we have shared memory locations, we might have processor 1 reading, you know, if it's variable A, if it's shared by all 3 processors, it might read and write A, it might read and write A, etc. If it's just like this picture, that's fine. But what if each of the processors has their own local cache? We might have a problem. Say there's some shared memory variable A. Processor 1 loads A. It's going to stick it in the cache. Actually, let me give it a value. What's your favorite number?
42.
Okay. So the answer to life, universe, and everything is here in our cache. Say processor 2 loads A, so we'll say this was 1. But then what if processor 2 changes the value of A to 7? We know that write-back caches are going to perform better, so we'd like that to be a write-back cache. We'll mark the cache block containing A as dirty. But what's going to happen if P1 reads A?
It's still going to read 42.
It's still going to read 42. And so in multiprocessor architectures, this problem is called the coherence problem.
But that's because it's reading in the value stored in the memory instead of the cache, right?
Well, that's here. So we said, okay, first it loaded A, it get the value from memory.
All right.
Then if P2 loads A, it's going to get the same value from memory. But then if it stores it, it's only going to store it to the cache because we'll assume it's a write back cache.
Exactly. Yeah.
P1 loads it, it's only going to load it from its cache.
All right.
Because it looks in the cache first.
So in that case, you have to find how to write in the memory.
Well, we could.
But even if it wrote it to memory, process 1 still would see that.
Still see as
It's still gonna-
because the cache.
Yeah, the whole point of the cache is that we're only looking in the cache if it's there because it's much lower latency than going all the way to memory.
Oh, okay.
And so we don't want to go all the way to memory, but we're going to have to we're gonna have to come up with an approach where we can guarantee that eventually P1 will see the update.
Preferably before it loads the value again.
Right, but we're not gonna worry too much about, say, like the race condition where P1 is reading A and P2 is writing A, and we don't have any locks or any other kinds of guarantee that the write's gonna happen before the read, because we'll assume that either, if it's a race condition, then either order is correct in terms of the architecture. It may not be correct in terms of your program, but if that's the case, then you should have
Put a lot.
yeah, you should have had some synchronization to make sure that there was that it was serialized, that there was some ordering. And so, in order to do that, we're gonna look at approaches right now. They're gonna take advantage of the fact that we have this shared bus. Now, I mentioned this is a super simple picture. If we look at processors today, we're not gonna see multi-core processors that are all connected just by a single shared bus. Why not?
It gets filled up.
Yeah, maybe this worked fine when we only had 2 processors in a dual core processor. But now, if you have a 16-core processor, what would happen if they're all connected to memory by a shared bus? What would all the processors be basically sitting around doing?
Waiting for memory.
Yeah, they're gonna be waiting for their turn to use the bus to go get values from memory. So we'll look at more modern interconnection networks, more modern maybe memory organizations. But the solutions to the coherence problems will build upon that same idea that we're gonna see in order to solve this problem, assuming we did have a shared bus. So if we can't just solve it via write through, I know we're out of time. One way that would solve this problem is if when processor 2 updated the value, somehow processor 1 knew that this block no longer had the correct value for its contents. What could we do? What single bit could we flip to guarantee that P1 would reload the block that contained A? That may have been too opaque, but I was
I
asking.
mean, in C, you can use the volatile keyword, which will tell it to reload it from memory.
Yeah, but I'm talking about in like our cache, not the dirty bit. If we're gonna say this block is no longer valid, if it's no longer valid, we'll flip the valid bit.
Yeah.
And so, we're gonna look at more sophisticated approaches, but the very first approach would be, whenever processor 2 stores, it could broadcast a message on the bus that, hey, I've updated the block with this particular address, and all of the other processors would snoop the bus, and the idea of, you know, the Snoopy neighbor, like in the 60s sitcom, the neighbor would be paying attention and would see that a write has occurred and it'll invalidate it. So we'll pick up talking about multi-processor caches. Snoopy neighbor reminds me, is anybody watching WandaVision? It's like the